rules. I know from experience that some teachers like to use shortcuts to get their students from where they are to where they need to be. And in mathematics, that takes the form of teaching rules or generalizations. The problem is, some of these rules or generalizations tend to fail as the students try to apply them to new ideas as they move up the grades. In fact, they can cause confusion and they need to be untaught later. So in this episode, I'm going to dive deep into 5 rules and generalizations that you should never teach. Let's take a look. One, to multiply by 10, simply add a 0. This is one of the most common rules taught in grade 3, and that's because it works. Well, in grade 3 anyway. 6 times 10 must be 60 because I simply added a 0 to 6, and I can extend it to 100 and 1,000. 6 times 100 must be 600 because I simply add 2 zeros to 6. Just add a 0 or 2. Simple. The problem is this does not work in the next year or two as they start learning decimals. Let's take a look at an example. 5 and 1/10 times 10. If I just add a 0, you get this, and the value of the number has not changed at all. So while third grade teachers may be making their job easier, and with good intentions trying to make it easier for their students, they're really just making it more difficult for them next year, and for the teacher who has to find extra time to unteach that rule. The real idea here is place value. If you multiply a decimal number by 10, you move all the digits one place to the left. So try using a place value slider like this, 3 and 5/100ths. If I multiply that by 10, I have to move all the digits one place to the left. And this sort of avoids that whole misconception of moving the decimal point. Now, what do I mean by that? I often hear teachers say, simply move the decimal point 1 or 2 places to the left or the right. But the decimal point must never move. It is always there to the right of the ones place, so we know where the ones or the units place are located. Now, you might just think this is semantics, but accurate language is critical when students are learning new ideas. So don't forget, the digits do the moving, the decimal point always stays still. Number 2, addition and multiplication make numbers bigger. This is one of my pet peeves, not because or just because the whole premise is wrong, but the whole idea of making numbers bigger, and I'll explore that aspect later. But this generalization is often made to help students understand what the operations do. If you add, you get more. If you multiply, you get lots more, right? Well, yes, it seems to remain true for whole numbers. For example, you can start with a group of 5 and add 3 and you get 8. And 8 is much more than 5. Or you can start with a group of 5 and then make 2 more equal groups of 5. 3 groups of 5 is now 15, and 15 is lots more than 5. In both cases, the total is much greater than the original 5 that we started with. However, I should point out that it doesn't apply to addition and multiplication involving 0. 0 is a whole number, but if I start with 4 and add 0, the sum, or the answer, is not greater. If I start with 5 and multiply by 0, well, the product is certainly no greater at all. It's actually now 0. Unfortunately, it also fails as the students move up the grades and start operating with fractions and integers. For example, consider this equation, 12 times 1/4. Well, you might say 1/4 of 12. Here the total, or product as we say, is now only 3. The same is true when both factors are fractions like this. The product in this example is less than both factors. It's best to avoid sweeping generalizations. Instead, help students explore what happens to the operations in certain situations. Ask questions like, what numbers are we adding and multiplying? Will it result in a greater number?
Notice my word or my intentional use of the word greater rather than bigger. In this situation, 5 is bigger than 7, but you cannot say that 5 is greater than 7. And number 3, you always divide the greater number by the smaller number. Now let's be honest, some students don't even read the word problem. They just look at the numbers and let the size of the numbers help them decide what to do. And there's even a cheeky version of this kind of student thinking, and it goes like this. If 2 numbers are close together, you subtract. If the 2 numbers are far apart, you divide the bigger number by the smaller number. If one number is bigger than the other, you multiply. If you haven't used addition in a while, you add. If the numbers are all whole and friendly, just guess one of the 4 operations and hope for the best. And if you've been in a classroom long enough, you've probably seen this kind of numbers first thinking in action. So this whole idea of dividing the bigger number by the smaller number comes from the early work with basic number facts like these. Here it works, and this is probably when the students start thinking, well, this is how division works. The problem is this rule crumbles as the students start solving real-world problems or they start working with fractions. For example, Jess buys 2 pizzas. She wants to share them among 4 people. How many pizza or how much pizza does each person get? So do you solve this problem by taking 2 and dividing it by 4? Where you could say taking 2 and splitting it into 4, and you see that they get half each. This problem is not solved by taking 4, the greater number, and dividing it by 2. And number 4, the longer the number, the greater it is. This generalization is often made in the early years as students are learning about place value. They soon observe that 237 is greater than 45 because it's longer. 1,500 is greater than 350 because it's longer, and so on. So the more digits, the greater it is, right? Well, not so. This whole generalization fails as students start to learn decimals. Look at this example. Which of these is greater? Some students may say 39 hundredths is greater because it has more digits. But 7/10 is more than 1/2, while 39 hundredths is less than 1/2. So even though 7/10 has fewer digits, it is still greater. A better approach would be to emphasize the value of the digit in each place, and visual representations such as area models will help students establish a mental picture of those values. Here you can see that 7/10 is greater than 3/10. And number 5, even numbers always end in 0, 2, 4, 6, or 8. I hear this one quite often, and it seems to work well. For example, 34 ends in 4, so it must be even. 107 ends in 7, so it's not even. It must be odd. But like so many other rules and generalizations, this fails as soon as the students encounter decimals. 4 and 2/10 ends in a 2, but it's not even. 3 and 75 hundredths ends in a 5, but that doesn't make it odd. This is because the rule only applies to whole numbers, but students are rarely told that up front. You can still teach a rule for identifying even numbers, but you need to be more precise or accurate with your language. An even number is a whole number that can be divided by 2 with no remainders. So there you have it. 5 rules or generalizations that may seem helpful, but can often do more harm than good. So this is what I want you to do. Number 1, forget the tricks, rules, and sweeping generalizations. Focus on giving the students the tools they need to reason, visualize, and make sense of numbers in mathematics. And number 2, as I've said many times in previous episodes, language is critical. You can prevent many misconceptions and confusions, if you like, simply by being more accurate and intentional with your language. And finally, if you've seen value in this episode, like, share, and subscribe today so you never miss another learning episode with me. See you next time.